Let's wait for a couple of minutes. After that, I will start. Okay, let me start. We see for Okay, so today this is the week 6 regression analysis problem solving session. Again, just like the other weeks. So we will start with the assignment questions for week 5 and then move towards the multicollinearity, which is the topics which are covered in week 6. So I will give some concepts of the multicollinearity. You may also look at the videos which are there in the NPTEL. There are 3 videos are there. Those are definitely more elaborative. So please watch those and understand the concept properly. Here I will also give some brief concepts of the multicollinearity, the important things which are required to solve the question. And finally, we will do one practice problem, which will consist of several questions. So that will help you to solve the next assignment. That is the week 6 assignment. Okay. So this is the total plan of today. So now, so we will start with the assignment questions. So these are the assignment questions for week 5. Just taking a PDF of that. So the important thing from the question is that there are 31 experimental asphalt pavements. So that actually shows that your N is 31. And if you look at the complete model, it consists of four regressor variables: x1, x2, x3, and x4. So if there are four regressor variables, it is understood that there are five unknown parameters, which are named beta naught, beta 1, beta 2, beta 3, and beta 4. Okay. So these are the based on the each and every combinations of models. The SS residual, the sum of square residual, is given for each and every combination. Okay, so four regressors, 16 combination, 2 to the power 4. We have seen that in the earlier classes. And here the partial F statistic based questions are being asked. So based on the given data, you have to, it is first asked, the first question asks that the value of the partial F statistic F1 in the presence of the other regressors like x2, x3, and x4 is approximately equal to. So this is the first question. Let's do it. Because a similar kind of question we have already done in the last class. We have done practice problems. So there we have already seen how to solve it. So, so the first question. So I'm not showing that SS residual table. I'm not writing. So I will just start. So it is F1 public 2, 3, 4. That is partial statistic of x1 regression in the presence of x2, x3, and x4. And it is already given in the question that n is equal to 31. There are 31 samples. So this is already given in the question. Now, what is the definition of this F partial? So it is SS regression based, not residual based, it is regression based. So it is 1, 2, 3, 4. You can write x1, x2, x3, x4, full model minus SS regression of 2, 3, 4. And finally, divided by the MS residual of the entire 1, 2, 3. Okay, so this is your definition of the partial F statistic. Now, I know that since we need to calculate this SS regression, we need to know what is the SS total because SS residual is already given. If we know the SS total, then we can easily find out SS regression in each and every case. So SS total will not change and it is generally defined as SS residual when none of the regressor variable is present. So SS residual of unknown parameter 1 where no regressors are present. So and what is that? So from the question you can see that it is 11.058. This is already given. Okay. So just I want to show one. See, for none of the regressors in the model, the SS residual is 11.058. And we know that from where we are writing this, we are writing this from the fact that SS total is equal to SS residual plus SS regression. But if SS regression is means there are no regressors, then it is nothing but the SS residual. So that is what we have used here, right? So this is the SS total which we have easily found out. So just I will write this is for the zero regression or non regressive present. Done. This is fine. Now next is to calculate SS regression and MS residual. Okay. So let's do one by one. Let us write SS residual 1, 2, 3, 4. Okay. This is already given in the question. I'm not showing every time. So it is 0.441, which is given in the question. And let's see what is. Therefore, if SS residual is known, we can calculate SS regression of 1, 2, 3, 4, which is nothing but SS total, which is 11.058 minus SS residual, which is given 0.441. This will give you 10.617, right? At the same time, we know that the degree of freedom of SS residual 1, 2, 3, 4. There are four parameters for regressions. Therefore, 4 plus 1, 5 unknown parameters. Right? We have already discussed at the starting. So there are 5 unknown parameters. Total number of observation is n, that is 31, minus 5 will be the degree of freedom. So it will be 31 minus 5, that is 26. So the degrees of freedom is 26. Now we need to calculate ms residual for the full model, because since we are talking about 1, 2, 3, 4 full model, let's calculate the ms residual because we need that. So what is the definition of the? We have seen that it is ss residual 1, 2, 3, 4 for all regressives divided by n minus 5, the degrees of freedom, which is 10.617 divided by 26. And this will give you 0.0169 roughly. This is the value of the ms residual. Okay, so this is done now. Yes. After this, we will need to find out this one, SS of 234. Let's do it. So for the SS of 234, let us first write it is given. SS residual of 234, which from the question it is already given. It is 1.041. Okay, this is also given in the question. Once it is given, you have SS regression. Okay, SS regression uh, 2, 3, 4, which is again same SS total, which is 11.058 minus 1.041. So what it will be? It will be 10.017. Okay. So SS regression of 234, 1, 2, 3, 4, and MS residual is already calculated. Just now you have to put in the uh, definition. So I will just put it here. So it is 10.617. That is for the full model. This is regression. For the 234, it is this divided by the MS residual, which is 0.0169. Okay. This will give you roughly 35.37. I have calculated this comes out to be 35.37. However, in the answer, it is given as 38.09. Okay, so this is the answer which is given. So, well, I would say that it is near to that, not exactly. As you can see that here, 38.09 is a unique value which we are getting because all other options are very far away from that. So, 35.37 and 38.09 are mostly approximated in this case. Okay, so this is 38.09. Okay, the next question is partial statistic of 2 in the presence of 134. So let's do it again in the same way. Okay, this is for question 2, which asks for partial statistics of x2 in the presence of 1, 3, and 4. The regressors 1, 3, and 4. And then what is the definition of that? Same SS regression, full model minus SS regression of now 1, 3, 4 divided by the MS residual of the again the full model. So already some part is already calculated, that is SS regression of 1, 2, 3, 4 and MS residual of 1, 2, 3, 4. So the SS regression of 1, 3, 4 needs to be found out. So for that we need SS total, which we already have, it will not change, and SS residual of 1, 3, 4. Already this is given, this is already known. So we can easily find out. So it is 11.058, which is fixed. we have calculated in the very beginning. This is fixed, and SS residual in this case is 0.581. So SS regression for 134, it comes out to be 10.447. Okay. So now F2 in the presence of 134 is 10.617 minus 10.477, which sorry, this is I think four. Okay, sorry, 477. Okay, 477 divided by the same value 0.0169. You can also write further some decimal places. So this comes out to be about 10.02. So none of the options actually matches, but I am getting it more close to, let's see, yeah, 8.25, because 3.61 is very far, 45.33 is no chance, 38.09 no chance. So 8.25 is the closest answer. Okay, so it is already given in the question approximately equal to, it is comes out to be 8.25. Okay, so this is the second question, which is done. Third question says that you start the backward elimination process. The first step, you consider alpha as 0.05. Okay, the regressor variable that is to be eliminated because it's a backward elimination process. So let's see. Okay, so question number 3, you will start with backward elimination given that alpha is equal to 0.05. First step of backward elimination. Backward elimination. Okay, so now the first step, actually, the starting step of backward elimination is that you assume the full model first. So there are four regressors. Not beta naught. So beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 and finally x1. This is the full model. You have to assume first the full model. We have discussed this. Okay. Now you have to remove something. So for that, what you have to do? You have to do some partial calculations. So one thing is that let's check 1 in the presence of 2, 3, 4. This is one of the options. Second is that check 2 in the presence of 1, 3, 4. Check 3 in the presence of 1, 2, 4. And check 4 in the presence of 1, 2, 3. Out of which these values are already been calculated. Although they are not matching with the answer, but I will write whatever values I have got. So it will not change much the results. Okay. So f of 1, 2, 3, 4 is calculated in question 1 and it is about 35.37, which I have calculated. F of 2 in the presence of 1, 3, 4 also we have calculated in the second question, which our calculation comes out to be 10.02. We need to calculate these two things. Okay. Where in these two things, you can clearly see that the SS regression 1, 2, 3, 4 and MS residual of 1, 2, 3, 4 is already calculated. So one thing which you need to calculate is as I will show. Okay. So what is required to calculate is T in the presence of 1 to 4. What is the definition? SS regression of 1, 2, 3, 4 minus SS regression of 1 to 4 divided by MS residual of 1, 2, 3. So now these are the couple of things. So out of which we have already seen this, we have already have these values. Only thing required to calculate it. I know from the question SS residual of 1 to 4, which is 0.450. Okay, so SS regression can be easily calculated. What is that? Just SS total minus SS residual. So it is 11.058 minus 145. And that yields 10.608 as the answer. Okay, so now I will calculate this F3124, which is nothing but values which we already have. 617 minus 10.608, which we now calculated, and divided by 0.0169. And roughly we get this as 0.5306. Okay, this is what we have got. Similarly, let us calculate another, which is 4 in the presence of 1, 2, 3. This is also we haven't calculated. Better to write all the steps every time so that you don't get confused. Okay, this becomes 1, 2, 3 and divided by ms residual of 1, 2, 3. Right. So again, two things are already known. We need to know SS regression of 1, 2, 3. For that, we need SS residual. So SS residual of 1, 2, 3 from the question comes out to be 0.498. Okay. So SS regression of 1, 2, 3 is 11.058 minus 0.498. That comes out to be 10.56. Right? So this is we have already got. So now see, yeah. So after we have got this, just we need to calculate 4 in the presence of 1, 2, 3. So this is fixed 10.617. We have already calculated minus 10.56 divided by ms residual, which is 0.0169. So this comes out to be about 3.36. Now, in the backward elimination, after calculating the partial F statistics, we need to see that which one is the smallest. And we found that out of all this 35.37, 10.02, 0.5306, and 3.36, we got this one to be the smallest. But we also need to check one more thing, which is the actual F statistic. How much? 0.05. 1 is the numerator degree of freedom is always 1, and the denominator degrees of freedom is 26. We have already seen that. This value comes out to be 4.23. Therefore, 0.53, which is the lowest, the minimum, is less than 4.23. Therefore, x3 can be removed. Okay, because it's an elimination process. So x3 is the regression which we can remove. So come back to the question. So which regressor variable you will eliminate? X3 is the accepted answer. So x3 has to be removed. Let's go to the next question, which says the second step. What will happen at the second step? Which variable you will be removing? So let's do it. Continue the process. Question 4. So the question 4 is that the second step of the backward elimination process. Here also you will have to use alpha is equal to 0.05 as the testing criteria. But now, after the first step, my model becomes now with three regressors, beta naught plus beta 1 x1 plus beta 2 x2 plus beta 4 x4 plus epsilon, because x3 is now removed. Well, after doing this, then what are the possible combinations of partial statistic we can have? That is x1 in the presence of 2 4, x2 in the presence of 1 4, and f4 in the presence of 1 2. These are the three possible partial statistics which we can have. Okay, so let's now compute each and everything. Now this time you have to calculate each and everything. Okay, so let's go ahead one by one. 1 oblique 2 4, which is SS regression of 1 2 4, the full model, minus SS regression of 2 4 divided by MS residual of 1 2 4. Okay, so this is the definition. Now let's calculate each and everything. So SS residual of 1 to 4 is 0.45, right? And MS residual, or let us calculate SS regression first. Okay, 1 to 4, which is uh, let me see. This is I think 9. No, not 9. It is 10.608. Okay, 10.608. This is the SS regression. Okay, just 11.058 minus 0.4. So now we have ms residual of 1, 2, 4, which is nothing but its residual of 1 to 4. But let's check the degrees of freedom now. This will be three regressors are now there. So 3 plus 1, 4 parameters. Instead of 5, now it is 4. Right? This is residual is 0.45 divided by 27, which is 0.0167. So MS residual is calculated for the full model. In this case, SS regression is also calculated. I need now SS regression of 2, 4, right? So this becomes SS total minus SS residual of 2. So this is fixed 11.05, it will never change. Now SS residual of 2, 4 is 1.218 given in the question. That gives you SS regression value as 9.84. Fine. And let us do one thing, because we need to also calculate SS regression of 1, 4 and 1, 2. Let us calculate those. Okay. So SS regression of 1, 4 is, I have already calculated, so I'm not doing entire calculation. It is 10.476, and SS regression of 1, 2 is 10.559. Okay, just SS residual for each individual case you calculate and subtract it from SS total, and you get this. Okay, so now just we will put the values and get the results. So F1 of the 2, 4, which I have already written the definition. This is the SS regression of 1 to 4, that is 10.608 minus SS regression of 2, 4, which we have calculated as 9.84 divided by the NS residual is mu, which is 0.167. This gives you 45.9. Done. F1 to 4 is done. F2 in the presence of 1, 4. Let's do it. So it is I have not written it. So it's 1, 2, 4 minus SS regression of 1, 4 divided by NS residual of the entire 1 to 4. Okay. So SS regression of 1 to 4, which is 10.608, we have seen. SS regression of 1, 4 is 10.476. 10.476. The MS residual we have already calculated for this case is this. Finally, we get 7.904. Go ahead with F of 4 in the presence of 1, 2. The definition remains regression 1 to 4 minus SS regression of 1, 2 divided by NS residual of 1 to 4. So here also 10.608 is fixed. SS regression of 1 to we have calculated 10.559. Isn't it? Yes. Divided by now the MS residual of 1 to 4, which is again 0.0167. This gives you 2.93. Again, check the minimum. So minimum is this. Okay, 2.93. Let's check for F.051, 27 this time, and this gives you 4.21. So 2.93 is less than 4.21. Therefore, x4 now can be removed or can be eliminated. Okay. So after the second step, we have eliminated x4. Right? X4. Okay. Fifth question says that what is the best regression model? So we have to go another step because x1, x3 and x4 we have already removed. Let's see whether x1, x2 is a good model or we can remove another. So let's go ahead. So this is question 5, where you have now y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus x1 because x3 x4 is removed. So here some little possibilities, that is 1, 2 and 2, 1. These are the only two possibilities which are present. X1 in the presence of x2, x2 in the presence of x1. What we require is SS residual. As you can see from the definition, you will understand now. These are things which are required. And so SS regression 1, 2, MS residual 1, 2. Okay, so let us do one by one. So SS residual 1, 2 is 0.499. Okay, from the question. This is given from the question. SS regression is nothing but 11.058 minus this. That is 10.559. I'm not doing it. And MS residual is SS residual divided by n, that is 31, minus two regressors means three parameters. So it becomes 0.499 divided by 20 gives you 0.0178. Okay, new MS residual. And also we require SS regression of 1 and SS regression of 2. This also can be calculated from the question, and this is actually 10.451, and SS regression of 2 is very small, 0.26. Okay. Now, based on this, we just put the values and calculate. So f of 1 oblique 2 is SS regression of 1 2 minus SS regression of 2 divided by ns residual of 1 2. Okay. So this gives you 10.559. We have calculated SS regression of 2 is very small, 0.263 divided by 0.0178 gives you 578.42. And finally, f of 2 in the presence of 1 is SS regression of 1 2 minus SS regression of 1 because it's known from the formula regression as the residual 1 2. This gives you 10.559 minus, here there is a change, 10.451 divided by 0.0177. This gives you 6.067. So we have to check because the minimum is this. Okay. So f.05, 1, comma 28. This gives you 4.20. Okay. So we can see that both f1 in the presence of 2 as well as f2 in the presence of 1 is greater than 4.20. Therefore, x1 and x2 will be our best replacement. Okay. So final answer is x1, x2. So as you can see in the question, the best replacement is x1, x2 for the fifth question. Now, 6, 7, 8 is particularly based on forward selection. Let's see. Yes. So let's do the forward selection and complete the assignment question. So first step, second step, and final. Okay. So these are the questions we know. So question 6. Let's do it. First they go forward selection. So alpha given to be 0.05 forward selection. So unlike the backward elimination, in the forward selection, we add regressor variables. Okay. So in the first assumption, we take it to be a zero order model. Nothing is there. No regressor is present initially. Now, then what are the possible F statistics? 1 in the presence of nothing, 2 in the presence of nothing, 3 in the presence of nothing, because there are 4 regressors, we know, and 4 in the presence of nothing. These are the 4 F statistics which you need to calculate. This is very easy because it's a full statistic. It's not a partial actually. It's a full statistic because no regressors are present. Okay. So definition of full statistic from the very beginning of the classes is nothing but S is regression of the one and divided by ns residual. So yeah, ns residual of the same. Let's do it. SS regression of one is 10.451. It is calculated in the same way. Okay. All SS regressions are calculated as SS total minus SS residual. Okay. Okay, so SS residual here is 0.607 divided by 1 regressor is present. So 2 will be the what you call as unknown parameters. We know that SS residual has n minus 2, simple linear regression. Okay, so with this we get 499.3. Okay, let's go ahead to in the presence of nothing. Okay, so Ultimately, the thing is same. I will just write it. This is regression of 2 divided by MS residual of 2, which is, let's write 0.263. We have calculated this in the earlier uh, question, and this is 10.795. The SS residual is very strong here. That's why SS regression is weak, divided by 29. This gives you 0.7065. F3 in the presence of nothing. Same definition, SS regression of 3 divided by MS residual of 3. So this gives you, uh, actually it's 0.395 divided by 0.367. Okay, so it's roughly 1.074. And finally, a 4 in the presence of nothing. The last possibility, regression of 4 divided by MS residual of 4. This gives you 9.536 divided by 0.052, and it is 183.3. Based on that, now we will have our F.05, the testing criteria, 1 comma 29, which is 4.18. Thing which is added is the highest one here. Okay, so this is the only highest one we have as compared to any other, and it is greater than this. Therefore, we add x1 is added. Okay, so for the sixth question, we can see that x1 is added. The sixth question, yeah, accepted answer is x1. Next is the second step. Okay, let's go ahead to the second step. Question number 7. Okay, so second step is same. So now we have, instead of beta naught plus epsilon, we have this. So possible combinations of F statistics will be 2, now new regressor 2 in the presence of 1 because 1 is already present, 3 in the presence of 1, and 4 in the presence of 1. These are the three things which we need to find out. So I have made a table for this. So these are the variable combination or regressor combination. This is the SS residual, and this is SS regression, and this is the MS residual. So I've computed each and every combinations, x1, x2, x1, x3, and x1, x4. These are required, as you can see. So SS residual is 0.499 for this from the question itself, 0.600, and this is 0.582. SS regression is SS total means 11.058 minus this comes out to be 10.559, 10.458, and this is 10.476. MS residual is, see, there are two variables, so it will be its degrees of freedom of SS residual. In these all cases, will be 31 minus 3, which is 28. So I have just calculated this. It is 0.0178, 0.0214, and 0.0208. Okay, these are already being seen. And for maybe, let me see. Okay, so we will see it later. Okay, fine. One thing is that for x2, x3, not required. Fine. So f of 2 in the presence of 1 is nothing but what? This is regression of 1, 2 minus this is regression of 1 divided by 1 is residual of 1. Okay. So I will just write, okay, this is 10.559, right? Minus this is regression of 1 is actually 10.451. Okay. In the same way, you have to calculate this SST minus SST residual, and this is 0.0178. This comes out to be 6.067. Let's go for F31 because in each and every case, SS regression of 1 is required. And I think SS regression of x1, I have actually calculated it, it is this, that's 10.45. Okay, so this becomes now SS regression of 1, 3 minus SS regression of 1 divided by MS residual of 1, 3. So I already given it here. So it is 10 point, we see 458, and this will remain same divided by ms residual is 0.0214. That is 0.3271. 3271. And finally, if 4 in the presence of 1, which is SS regression of 1 4 minus SS regression of 1 divided by MS residual of 1 4. So it's 10.476 minus 10.451 divided by 0.0208. This gives you 1.20. Okay. And what is the criteria? As given, it's 0.05, 1, comma, 28, which is 4.20. So highest has to be added. Highest is this. So x2 has to be added. Can be added. Okay. So if you look at the second question, it's x2. Okay. And final is the best regressor model. So let's quickly look into it. That is the last question. Question in. So this is a bit lengthy assignment. If you do everything step by step. Okay. So right now we have the model beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. Okay. So possible combinations are which were not there. So 3 in the presence of 1, 2 and 4 in presence of 1. These are the two possible combinations. Let me quickly write down MS residual for 1, 2, 3 because here in this case it's 0.498 which is the SS residual divided by 27. Why 27? 3 regressors. So 31 minus 3 plus 1, 4. Okay. This gives you 0.0184. And let me write also this residual of 1 to 4. For this case, it is, let's see, it is 0.0168. Okay, let me quickly write. This is regression of 1 to, which is very necessary, which is 10.559. We have already calculated earlier. And we also need regression of the full, that is 1, 2, 3, which is 10.56. And this is regression of 1 to 4, which is 10.60. And now just the definition. So F3 in the presence of 1, 2 is SS regression 1, 2, 3 minus SS regression 1, 2 divided by MS residual 1, 2, 3. Putting the values, we get 10.56 minus 10.559, which will remain fixed, divided by 0.0184. This is 0.0543. Let's do 412. Again, for the last time, I will write this. So it's 124 minus SS integration of 1 2 divided by MS residual of 1 2. This gives you 10.608 minus 10.559. This fixed. And MS residual will change, which is 167. This gives you 2.9. Okay. And criteria again to satisfy that 0.051 in the numerator, denominator will be 27, and this is 4.21. So none of the regressors or none of the possible F statistics, whether it is 3 in the presence of 1 2 or or 4 in the presence of 1 2, both are less than 4.2. Therefore x1 x2 is the best regression. Okay, so let's check. Yeah, x1 x2 is the fine. With this, we complete the assignment. So I have made a detailed solution of the assignment questions. Okay, I hope it is clear. And we have also solved so many questions in the last class. So it will be easier for you. Okay, so now we will move towards some concepts of multicollinearity, and we will look for one practice problem at the very end. Okay, so next, let's see, for 45 minutes, if we can, we just revise the concepts of the multicollinearity. Okay, after that, we will try to solve the problem. It is a short problem which is there, it is also present in the practice questions. So I will solve that one. Okay. Okay. So I remember in while we are talking about multiple linear regression model, there a question is being raised that what will happen while we are computing uh, the beta, okay, collinearity. This is the concept of the week 6. Okay. So we know that the beta hat in the multiple linear regression model, that is x dash x inverse x dash y. This dash has the transpose, and x and y have its their own meaning. But a question is being raised by someone that this x dash x inverse, what will happen if the inverse does not exist or the determinant is 0? That is what the concept of multicollinearity means. At that time, also, I have just shown, I've just told that if there is a linear dependence between the uh, regressor variable, then only it is possible that the determinant is 0, because that is the property of determinant, right? So, if the determinant is 0, then it's a singular matrix, its inverse will not exist. So, for that, reason is multicollinearity is there, and here in this week 6 lectures which are already present in the NPTEL videos, it tells us, it shows that what are the problems or what are the detection techniques through which we will detect that yes, there is a multicollinearity present in a particular data set, and what we will do to overcome that. Overcoming is very little mentioned by adding number of samples and all those things. So we will look one by one. Okay. So multicollinearity is the concept deals with this. Okay. So let us just define first what is multicollinearity. It's easy to understand. So when two or more regressor variables, that's why we are talking about multiple linear regression model. So it's MLR. Okay, multiple linear regression model. More regressor, okay, two or more regressor variables. When two or more regressor variables are strongly correlated or linearly dependent or linearly dependent, the thing which arises is that in your y is equal to x beta plus epsilon, this beta hat which I was talking about, this x prime x inverse x prime y, this definition, this thing does not exist. So when it is very strong, if very strong correlation is present or linear dependence present, you will find that x dash x inverse will not exist. Okay, this is the problem. So what happens is that the determinant of x prime x, this matrix, goes to 0. And when determinant is 0, you know that the inverse does not exist. So this is the concept of multicollinearity. Okay. Okay. So if I have to write, so if this x prime x is a singular matrix, which I have written here, if it is a singular matrix, which is determinant is 0, we can't perform inverse. Okay, so this is the concept of multicollinearity. So when there is a dependence between the regressor variables, there is a possibility that the inverse might not be calculated. So for that, and if this kind of problem exists, then how we can detect it? So those are the things which is discussed in this particular uh, week's lecture. Okay. So one of the examples which is given in the lectures, I have just taken it, and I think it is present in the assignment questions as well. So x1, x2, x3, and there is a y, of course. So this is the problem which is given: 2 minus 7, 11, 4, 3, 5, 7, 1, 13, and 8 minus 1, 17. Okay. And it is 81, 88, 94, 95, and 120. Okay. So in this case, this clear connection, if you just add these two, okay, if you just add these two, x2 plus x3, so what it will be coming? So it will be 4 minus 2 will be 2, 11 minus 7, 4, 5 plus 3 is 8, 7, 13 plus 1, 14, and 17 minus 1, 16. So if you now multiply 2 into x1, it is exactly similar to this. And we know that the property of a determinant, that when you have two rows or two columns are dependent on each other, your determinant goes to 0. That is what the multicollinearity problem states. So here actually the thing is that x1 is x2 plus x3 divided by 2. This is what the thing. So x1 here is not linearly independent. X1 is not linearly independent. And therefore, it is possible that this x prime x is inverse, or x prime x is a singular matrix, or inverse does not exist anyway. Okay. So this is the multicollinearity problem, an example of the multicollinearity problem. Okay. So let's see, let's discuss. It's already been discussed. I have just taken the concept so that we can solve the questions. So what are the problems of multicollinearity? Let's, what are the problems of, you can say, the detection of multicollinearity? I will skip something. I will put most of the things I will try to put, but it's a huge uh, concept, so I will not be able to show everything. So the first one is that strong multicollinearity between regressors resulting larger variance. Okay, larger variance or covariance, anything. I mean, it's both or covariance. Okay, of regression coefficient. Whose variance? The regression coefficient. Beta 1, beta 2, beta naught, those things. So in general, we write yi, you know, because from the multiple linear regression model, we generally write this as beta naught plus beta 1 x I1 plus beta 2 x I2 plus epsilon I, where I are the number of samples and 1 and 2 represents the two regressors. That is considering two regressor models. Okay, so I is generally varying from 1 to n. Okay, and we know that x is generally written as all 1 in the first because beta naught is present here, and then you have x11, x 21, and so on up to xn1, and this is x12, x22, and so on up to xn. This is your right. Now, to show that this is this regression coefficients, larger variance and covariance, a standardization technique is used. Okay, that standardization technique is popularly known as centering and scaling. And for entire multicollinearity detection, we generally use this centering and scaling. Today also, when we solve the problems, we will use this particularly, this concept, centering and scaling of regression data or yeah, obviously regression data, because not only for the regressions but also for the dependent variable like y, we do the same thing. Okay. So what we do is that the definition of this is that x, small x, okay, I1 is actually capital X I1, the capital X which we have defined here. Okay. So I1 minus x1 bar. This is actually called the centering, the numerator. It is centered about its sample mean, x1 bar. Okay. So what I mean is that this is suppose x1, you have x 1 1, x 2 1, and so on up to xn1. Okay. So you take the sample mean, which is x1 bar, and each element is subtracted from the sample mean. So this is the centering. Okay. And next is the scaling. Scaling means something you multiply or divide. Okay. Scaling is through the standard deviation. So it is root of S11. How, so what is S11? What is X11? Let me write it. Okay. So X1 bar is 1 by n. Let us say that n is the number of observations. Summation I going from 1 to n. X I1, which is I am 10. Summing all and divided by the number of observations n. Okay. And what is S11? Incomplete standard deviation definition. We are not dividing it with n in this case. It is just the summation of the, so I is equal to 1 to n. It's just the summation. Okay. So xi1 minus x1 bar whole square. This is also a variance, kind of variance, but in case of variance, we generally divide it with n. But here we are not dividing it. Okay. So this is the definition of x11. This is x1 bar. So this is your centering and this is your scaling. Okay. So this is how each and every regressor variable is written. So similarly, xi2, the second regressor can be written as the actual xi2 minus x2 bar divided by root over s22. So again, if I have to write, x2 bar is 1 by n because n is same. I is equal to 1 to n x I2 for the second regressor. And S22 is summation I is equal to 1 to n x I2 minus x2 bar whole square. This is the definition. Okay. And as I have told you that we will not be doing it for the regressor variables. We will also be doing it for the dependent variable, the response variable y. So for y, we have small y of I, which is yi minus y bar, this should be capital, divided by root of sy1. Okay. So similar definition is same. Y bar is I 1 by n. I going from 1 to n. Y I. Simple. And what is syy? Let me complete it here only. This is summation. I is equal to 1 to n. It is yi minus y bar whole square. This is what. Okay. And this is, I think, nothing but the SS total. Okay. Yes, YY and SS total is same. So this is the kind of a standardization technique which we use. Okay. Now what the new variables we have, small x1, small x2, and y, these are now centered and scaled, centered around the mean value and scaled by the standard deviation. Okay. Now, if you do x1 bar, since it is already centered around its mean, so x1 bar will be what? Will be 0. Right? X2 bar, it will be 0. Y bar, everything, it will be 0. Right? Now, if you come back to your original equation of multiple linear regression model, so it is beta 1 x1 original. This is original, okay? X2 plus epsilon. This is the original MLM. We take its estimation as beta naught hat plus beta 1 hat x1 plus beta 2 hat x2. That's all. Here, using normal equations and all, we can write beta naught hat as y bar minus beta 1 hat x bar minus or x1 bar beta 2 hat x2 bar. This is what we can write from the normal equations. Okay. Now, for this centered and scale technique, if you write this for centered and scale data, okay, centered and scale data, if you write this beta naught hat, what it will be? Small y bar minus beta 1 hat x1 bar minus beta 2 hat x2 bar, right? No, not x2 bar. I've taken all, I think. Yeah, right, correct. Okay, x1 bar and x2 bar. So y bar is what? 0, x1 bar 0, x2 bar is 0. So beta naught hat goes. Therefore, now my y is actually beta 1 hat x1 plus beta 2 hat x2. Now this capital X1 and X2, what I am writing, or the Y I am writing, these are all in capitals I am writing, but these are actually the small y, X1 and X2. Okay, so this is the centered and scaled model of the MLR original which we have. Okay, so this is, so right now if I am writing X1 and X2, we are meaning now centered and scaled. Okay, don't confuse. Fine. So this is what you now look into it. If beta naught hat is zero, if beta naught hat is zero, that means the thing which we write that x, we generally write what? There will be a column of one. This column of one is for the beta naught hat, but in the center and scale, beta naught hat is zero. So once we will not write, we will only write the x's. So x11, small x, x 1. Now my new capital X is this small. Okay. So this will be x in 1. These are the centered and scaled samples. Next, x12, x22, dot up to xn2. That's all. Okay. Not writing 1. 1 is not written because beta naught hat is now 0 on center and scale. Okay. So now, okay. So there will be a y also, which is nothing but small y1, small y2, and so on up to small y. That's all. Correct? So the normal equation will be same. It will not be differing, but x dash x beta hat is equal to x dash y. But we have to remember that this x is now the centered and scaled. This y is now the centered and scaled. That has to be remembered. So beta hat's definition will be same, but see, this definition will be same, but consists of different things, centered and scaled parameters. Okay. So in this x prime x, which is there, x prime x. If you now multiply these two, this x you take its prime transpose and multiply it, x prime x, this will give you the correlation matrix. Remember, this will be only for correlation matrix. This is true only for your multiple linear regression model with two regressor variables. After that, you generally have to take what you call as the coefficient of multiple determination. So correlation matrix. This is true for two regressors. In fact, for more than two regressors also, you can use the correlation matrix, which is easier to do. So you can do it, but mostly we generally do it for the two regressor model, which is shown here. Okay. So I will do it for the two regressor model, and mostly the assignment questions are also based on that. Okay. So let's see. So this x prime x correlation matrix can be written as 1. This R is the correlation of one first regressor with respect to 2 with respect to 1, which are nothing but similar. And this is 1. This is the correlation matrix x dash x. Okay. Okay. Now, what was the normal equation? X dash x beta hat is equal to x dash 1. Okay. So we can write this as 1 R12. I will write each and everything. R21. This is 1. Beta hat is now beta 1 hat and beta 2 hat. No beta naught. And x prime y is nothing but the correlation of first regressor with y, correlation of second regressor with y. Okay. So R12 is nothing but sample correlation between regressors 1 and 2. Similarly, R1y is sample correlation between x1 and y. Let me write x1 and x2. And R2y is same sample correlation but between x2 and y. Okay, so this is the definition. Okay, what is Rxy? The correlation definition is nothing but summation I going from 1 to n x I minus x bar. This is the general definition of the correlation, where the upper part is nothing but the covariance divided by the lower part is the standard deviation. Okay, where Sx and Sayy are the variance. Okay, this is the correlation definition. This is correlation. So if you now multiply this x prime and x, the way we have centered and scaled, if you multiply them, matrix multiplication x prime x, you will get a correlation matrix. Okay, fine. So x prime x, therefore assume that we have got the correlation matrix. This we will see in the practice problem. We will see this R12. So this is R21 and this is 1. Okay. Now x prime x inverse will be what? Divided by the determinant. And so determinant will be what? Determinant of x prime x. How much it will be? So it will be 1 upon, oh sorry, not 1 upon. So it's 1 minus R12 square. You can write. Because R21 is actually equal to R11. Why? Because we have two time series x1 and x2. So if you correlate 2 with 1 or 1 with 2, it's same. Okay? Look at this definition also. It is same. Nothing will change. So this will be therefore written as, and how to write inverse of a 2D thing. So it is A, B, C, D suppose. If you have to take its inverse, it will be 1 upon AD minus BC. You have DA minus B minus, this is how it is. So it is 1 upon 1 minus R12 square. This is minus R12 divided by 1 minus R12 square. You can write it R21, it doesn't matter. 1 minus R12 square, and this is 1 upon 1 minus R12 square. That's all. So this is x dash x inverse. Okay. So if you write now beta hat as x prime x inverse x prime y, so you will get the beta hat as this. So it is, I'm just writing 1 minus R12 square. This is minus R12 upon 1 minus R12 square. This is minus R21 divided by 1 minus R12 square. And this is 1 upon 1 minus R12 square. This times x prime y is R1y. Just take the correlations and write it. Okay. That's all. And from the same multiple linear regression model, we have variance of beta cap j or a particular beta. The variance extent is, or variance is x prime x, the jj element. Okay, x prime x inverse. So let us say variance of say beta 1 hat. Okay, so it will be sigma square x prime x inverse of 1 1. Okay, so this sigma square will remain. Okay, and x prime x inverse 1 1 is this for this case. Okay, two variable now. So it will be 1 minus r12 square. Now, if there is a strong multicollinearity, your dependence is high. The linear dependence is high. So R12 will tend to 1. Why modulus? Because correlation can have minus as well as plus value. That's why a modulus is given. So if it is tending to 1, R1 square, R12 square will be tending to 1, then what will happen? The denominator becomes 0. Therefore, this variance of beta 1 hat or beta 2 hat if you take, it will tend to infinity. Okay, so this shows that there will be a large variance of the regression coefficients, beta 1 hat or beta 2 hat you can take. And for covariance, the definition will not change much. So this becomes sigma square. This is x prime x inverse the of diagonal elements. Okay, like 1 2 2 1. Okay, so this will be minus sigma r12 divided by 1 minus r16 square. So this is the off diagonal element, this one or this one, anything. Okay, in this case, it will can tend to plus minus infinity depending on what is the value of r12. Okay, it depends on this. Okay, whether it is positive or negative, and if r12 tending to plus minus 1, your thing the covariance will go to plus minus infinity. So this is important. Now, for what will happen for more than two regressors, because I have told you that this is for two regressor model. For more than two regressors, we write with x prime x inverse diagonal elements instead of correlation. We write it 1 minus rj square. Okay, this rj is your rj square is your coefficient of multiple determination, but there is a thing here, this coefficient of multiple determination. Okay, so j can of course go from 1 to k minus 1, because if there are k minus 1 regressors, which we generally take as an assumption. But what is this coefficient of multiple determination? So this rj square is coefficient of multiple determination between what? Between xj element with all other. Okay, all other elements. So it's between xj and x1, x2, so on up to xj minus 1, then xj plus 1, except for xj, all other variables, xj minus 1. Okay, so xj with all other regressors. So you have to make a model as that xj is a function of x1 multiple linear regression model only, MLR, up to xj minus 1, next xj plus 1, comma xk minus 1. This you have to fit a model here with this as a response and all other as a regressive variable. Calculate your SS residual for that model. Okay, and that is the what is the definition? SS residual divided by SS2. That's all. This is how you will calculate. Okay, why for two regressors you are using correlation and for others you are doing RJ square, the coefficient of multiple determination? Because R, the correlation is actually for the two variables which I have defined. Look into it. Okay, so this the R X Y. Only for two time series you can do correlation. You cannot do it for more than that. Okay, so that's why we have to shift to RJ square. And so when I have shifted to RJ square, uh, so for strong multicollinearity, the condition is that strong multicollinearity, RJ square generally tend to 1. We have seen it. Okay. And therefore, the variance of beta G hat is tending to infinity. Okay. Variance of beta J hat tends to infinity. Okay. So when we have talked about this, let's go to a criteria which is called, let me write it in color. So this is one of the criteria. Okay. So detection criteria. Let's write it detection criteria number one. Criteria number one, which is variance inflation factor. Variance inflation factor. VIF. So VIF, the definition is quite similar, which is VIF of say particular regressor beta I hat is sigma square x prime x II is sigma square on 1 minus Ri square. Okay. So for two regressors, the same thing is sigma square on 1 minus R12 square. Okay, the correlation. This is correlation. This is correlation. This is coefficient of multiple determination. The same way has to be calculated. Okay, so now we define, this is actually not the variance equation. This is the variance. Okay, this is variance. But VIF is for ith regression is 1 upon 1 minus R square, not the sigma square. Okay, this. And VIF for two regressor model only is so greater than two regressor. And this is for R12 square for two regressor. Okay. So this is the thing. Now, what is the criteria? The criteria is that if your VIF, whichever I or whatever you say, if VIF is greater than equal to 5, it indicates multicollinearity. Okay. And VIF, if it is greater than equal to 10, it indicates strong or certainly multicollinear. So certain about the multicollinearity. So you can say that VIF greater than equal to 5 is more of a near multicollinearity and this is certain multicollinearity. Okay, so these are the two conditions for the VIF. Two conditions for VIF are this. Okay, so one detection criteria we have discussed. Let's go ahead with the other concepts. Let me just complete the other things, which I will not, just I will write down. Okay, so other problems, one of the problems we have discussed that variance and covariances are large for the regression coefficients. Other problems, we come back. So the second problem is that and just write it down. So you can refer to that lecture notes. Okay, collinearity tends to produce, everything is difficult to complete here. So least square estimate beta that are too far from the actual parameter beta. Okay. So when we estimate the beta hat, in case of multicollinearity presence, beta hat becomes too far away from beta. Okay. This is the second. Third is your model coefficients with negative sign when expected positive. When positive sign is expected. So if you expect that the beta naught, beta 1, beta 2, or beta 1, beta 2, they are of positive sign, you will get a negative sign. Okay. So that is the problem of multicollinearity. Fourth, global left test, writing in short, global left test has higher significance. This is very well explained in the lecture. Okay, high significance, but partial tests, partial left tests. So none of the partial left tests are significant. None of partial left tests are significant. Okay, this is another. And the last problem is that different model selection, we have seen how many model selection things are there, like forward selection, backward elimination. So different model selection procedures yield different models. So we have seen these, okay, different models. So there are several model selection procedures. It is possible that each and every model selection procedure will yield you different best regression models. Okay, so these are the problems. Now, one of the detection criteria I have already told you, which is the BIS. Now, other detection criteria, there are two other detection criteria which I will show now. And once we finish this, we will come to the questions. Okay, so the first or okay, the second detection of multicollinearity, a very simple detection technique is that examination. The second part is examination of correlation matrix. Of correlation matrix. So you find out Rij. Of course, for two regression, you will find out if this is greater than zero point 0.9. I've taken a mod because it can be plus or minus. Then it indicates it's just a threshold criteria. You can see indicates multi-collinearity. Okay, this is one of the things. And as I have told you, this is the of diagonal elements. Of course, because diagonal elements are generally one. Okay, but as very nicely shown in the lecture notes, there is a problem. If you solve the correlation matrix, you might not find it zero point 0.9 value, maybe zero point 0.5, zero point 0.4, something. But you cannot guarantee that if there is a multicollinearity presence or not. Okay, so this is another detection technique. The third, which is very important and very useful detection technique, is the eigensystem. So whenever is required to detect the multicollinearity, use this process. This is the best method. Okay, best. So eigensystem analysis of what? Always eigensystem analysis of experiments, because here the inverse exists. So multicollinearity comes because of this inverse. So okay, eigensystem analysis of experiments. We will do it in the practice problem. So first you have to calculate eigenvalues using the linear algebra technique, so of x prime x. So if there are k minus 1 regressors, we'll have k minus 1 eigenvalues. And let those eigenvalues are lambda 1, lambda 2, so on up to lambda k minus 1. Correct? We define a number called the condition number, which is denoted as k is lambda max divided by lambda min. See, for two regressor model, you have one lambda max, another is lambda min. Okay, but for k minus 1 regressors model, you have to check each and every part. Okay, So now if lambda mean here is very close to 0, then see k, the condition number will tend to very large value or infinity. So criteria is that whether criteria for detection of multicollinearity is that for in this case, if k is less than 100, no serious problem. Okay, no serious problem of multicollinearity. K in between 100 and 1000, you have moderate to strong problem or moderate, yeah, okay, moderate to strong multicollinearity problem. But if K is greater than 1000, a very severe multicollinearity problem is there. Okay, so this is another criteria of detection. But for regressor, two regressors, it is fine to define like this. But what about when you have k minus 1 regressors? So for k minus 1, k minus 1 is the number of parameters. Okay, k minus 1 regressors. Check for largest lambda or eigenvalue. Okay, so k1 will be lambda max divided by lambda 1. K2 will be lambda max divided by lambda 2. So on, whatever you wanted to see. K of k minus 1 is lambda max divided by lambda k minus 1. Now, whichever k number is greater, that will be the this is the k indices. These are k indices. Let me write. These are k indices. Okay. So this will help you to understand that which due to which regressor you are getting multicollinearity. Due to which regressor multicollinearity is collinearity is present. Okay. This is yeah. And another thing is that which is related to this is that we can write x prime x is equal to t dt. D is the diagonal matrix with diagonal elements as eigenvalues, and this T matrix is the eigenvector matrix which consists of T1, T2, and so on up to Tk minus 1, where T1 is the corresponding to the lambda 1 eigenvalue, the eigenvectors. Okay, so this is actually k minus 1 cross k minus 1 matrix. Okay, so based on this, we can write that a1x1 plus a2x2 and so on up to ak minus 1 is k minus 1 is 0. So the nature of linear dependence can be found, can be found. That's all. These are the important techniques through which, so we will see this. We will see how to do this. Okay. Let me just last couple of things before going to the practice problem. It's a short practice problem. We will do it. Each and everything will be dealt with. So how to deal? So deal with multicollinearity problem. Okay. Number one is that you increase the sample. So additional data has to be given. So increase the sample is number one. Number two is that remove regressor from the model, whichever is you think that it is depending. Remove regressor or regressors from the model. This is another technique to do. Number three is collapse variables. So what happens is that, say if you have x1 is say 2x2, so it's better to take any one, remove this, okay, collapse variable. And there are many other techniques. One thing I have seen that in the assignment questions, people talk about one of the questions has something to do with principal component analysis. So what is principal component analysis? I give short description so that you can understand and try to solve the assignment question. I will not tell you. So it is that suppose you have x1 and x2 and you have some kind of a dependency. Right? See, there are some data sets which are present over there. Okay. Principal component analysis, what it does is that it, if I draw an axis here, say Z1, and it mutually perpendicular axis, say Z2, such that the Z1 and Z2, the new variables which we have based on this new axis, this Z1 and Z2 correlation is 0. Okay. So principal component analysis is from a dependent domain or from a correlated domain, which is x1 and x2, which shares a good correlation. It transforms it into an uncorrelated domain, z1 and z2. Okay. This is the meaning of principal component analysis. It will help you maybe in the problem solving while solving the assignments. Okay. With this, I will end the contents. Now we will go for one of the practice problems. Okay. So just a minute. I will start. Okay. Let's see what is the problem. Yeah. Okay. So the practice problem is that you can find it in the week 6 practice questions. So the question is, let me write. So you have two regressor model, y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus xi. Okay. And you have been given x1, x2 and y. Okay. So you have -2, -1, 0, 1, 2. And x2 is -4, -1, 0, 1, 4. This is 12, 9, 9, 14, and 16. So this is the samples which are given. Okay. So the question says that center and scale the x1, x2, and y columns. Okay. You have to center them. Let x1, x2, and small y be the center and scale, center and scaled columns. Now fit the model y. This is not small y. Okay. Beta 1 x1, of course, because when you center and scale it, beta naught will be gone. Plus beta 2 x2 plus xn. Okay. So question is that find the estimate of estimate of beta 1 and beta 2. So I'm combined both the questions. Okay. So first you have to center and scale this x1 and x2 and y. Let that be x1, x2 and y, the small one, and you fit a model and find the estimates of beta 1 and beta 2. That's all. That is what you have to do. Let's do the centering and scaling. Okay. Let me write certain things. Let's say this is x1, which is -2, -1, 0, 1, and 2. Okay. So let's see what is your x1 bar. So x1 bar, as you can see, is 0. Well, so it is already centered about 0. So you don't need to worry. Next, what we do is that let us write x1 minus x1 bar square, because this is required for S11. So it will be minus 2 minus 0, because x1 bar is 0. So it's just one x1 square minus 1 square, 0 square, 1 square, and 2 square. So this is 4, this is 1, this is 0, this is 1, and this is, sorry, this is 2 square, right? This is 4. So now, if you sum it, x1 minus x1 bar, or xi1 minus x1 bar, so this comes out to be 4 plus 1 5 plus 1 6 plus 4 10, right? So S11, which is this, is 10. Great. Let's do the same thing for x2. This is minus 4, minus 1, 0, 1, 4. Again, if you do x2 bar, which is equal to 0, 4 plus 1 5, and this is 0. And x2 minus x2 bar square will be simple, therefore minus 4 square, minus 1 square, 0 square, 1 square, and 4 square. So how much it is? 16. This is 1, this is 0, 1, 16. 16, 16, 32, 33, 34. So S22 is 34. Correct? So we have found out S11, we have found out S22, X1 bar, X2 bar are both zeros. But at the same time, we have to do for y also, right? So y is what? Y is given as 12, 9, 9, 14, and 16. So let's do y bar. How much it is? 16 plus 14, 30, 39, 48, 12, 60. 60 divided by 5, which is 12. Right? Y bar is 12. And what I did here is y minus y bar whole square. So 12 minus 12 is 0 square. 9 minus 12 is minus 3 square. 9 minus 12 minus 3 square. 14 minus 12 2 square. And 16 minus 12 4 square. So this becomes 0. This becomes 9. This is 9. This is 4. And this is 16. So if you add them now, so it becomes SYY is 16 plus 4, 20, 29, 38. Right? SYY is 38 and Y bar is 12. So X1 bar, X2 bar, S11, S22, Y bar and SYY are already found out. Only thing now we require to do is that we have to say what is the X1, small x1. So each and every term we do and finish it. Okay, so let me again write x1 again. So this is minus 2, this is minus 1, this is 0, 1, and 2. Right? So x1 will be what? It will be minus 2. So each and every time the x1 bar is 0, right? X1 bar is 0. So I don't need to write anything, but divide with S11, which is 10. Minus 1 by root 10, 0 will always be 0, 1 by root 10, 2 by root 10. So how much it will be? 0.632. This will be 0.316. This is always 0. This is minus 0.216. And this is minus 0.632. Done. This is x1. Let's go ahead for x2, small x2. And x2 bar is also 0. So what was x2? Minus 4, minus 1, 0, 1, 4. So this will be minus 4 minus 0 by root 34 with 34. Yes. Right? Is 2, 2. Yeah. So minus 1 by root 34. 0 will always be 0. Root 34 and 4 by root 30. So how much it will be? I have calculated already. So it is 0.636, 0.1715. This is 0. This is 0.1715. And this is 0.686. As you can see, if you make x1 bar, this will be 0. As you will do x2 bar, this will be also 0. Let's do y bar. or let's do y. Okay, so this small y was what? 12, 9, 9, 14, 16. But what happens here is that, uh, let me check. Yeah, this comes out to be, I'll just quickly write it, minus 0.486. This will be minus 0.486. This will be 0.324, and this will be 0.648. Okay. So how I've done it? So it's 12 minus 12 divided by root of 38. In same way, 9 minus 12 divided by root 30, like that. Okay. So y is also found out. Great. After we have done x1, x2, and y, they have asked to calculate beta hat. Okay. So let's do beta hat, which is x prime x inverse x prime y. Okay. So x prime x, as I have already told you, for this case, x prime x for center and scaling case, this is nothing but a correlation matrix. So 1, R12, R21, and 1. Okay. So, but even if you don't do it, okay, if you just write x, let's write x, okay, let's write x, it is minus 0.682 minus 0.686. Let me just complete. Minus 0.316, 0, 0.316, and 4.632. Here also it is minus 0.1715, 0, 0.1715, and 0.686. Okay. So it will be a 5 by 2 matrix. What about x prime? Because you need x prime x, right? So it will be just the transpose. So let's also write this minus 0.316. I think it is 3, 0, 0.316, and 0.632. This is minus 0.686, minus 0.1715, this is 0, 0.1715, and 0.686. This is 2 by. So if you do x prime x, you actually get the correlation matrix, which has 0.99856, 0.975492. This is also 0.975492, which will be same, the correlations. And this is 1.00000165. Okay. As you can see, these are roughly 1, and these are the correlation coefficients between the small x1 and small x2. Okay. So this is your x prime x. Now, if you have to calculate it inverse, we will do it. So let's do x prime y. So x prime y, I have already calculated. It is 0.665496, 0.583443. Okay, I have already calculated. So x prime y is known. Now we need x prime x inverse. So x prime x inverse is, you write the determinant. So if you calculate the determinant of this part, it will be just 1 minus 0.975492 square. Okay. So that comes out to be nearly 0.0469. And inverse in case of 2 by 2 matrix is easy. So I can write 1 1 minus 0.975 492 and minus 0.9745. Sorry, this one. So it is minus 0.975492. You can keep it 1 or you can keep it 0.99 something, whatever it is there. This is experiment inverse. And what is your beta hat therefore is, according to the definition, experiment inverse x prime y. Okay. So which is 1 upon 0.0469. The same thing, and x prime y, which is 0.0469. 665,496.58344. Once you do it, your beta comes out to be, let me see what is the beta, is 2.0506 and minus 1.416. These are the beta values. Okay. Here we have only used the multiple linear regression format and just calculated the beta, but using the centered and the scaling table, which is given in the question. So these are the now my new beta 1 and beta 2. So this is your beta 1 hat estimated and this is your beta 2 hat estimated. So these are the first two questions. Okay. Next question is calculate variance inflation factor VIF for the first regressor for beta 1 hat. Okay, for the first regressor. We know that for a two regressor model we have seen, okay, for the first regression coefficient model is 1 upon 1 minus R12 square. Okay, the diagonal element, right? So this will be nothing. I know that R12 square is nothing but 0.975492 its square, because why this, because this is your R12, correct? This is your R12. Let me just check once. Formulation. Yeah, this is your R12. So I need what? R12 square. So R12 square is nearly 0.9525. Okay. So just calculate VIF therefore is 1 minus 1 minus 0.9525. This gives you nearly 21.0. So this is the variance equation factor. Okay. So it's greater than equal to 10 at least for this case. Okay. So this is the question. Next question is, this is how the questions will come. Okay. Next question is, what is the determinant? What is the determinant of the correlation matrix? Correlation matrix is X prime X. So we know the correlation matrix determinant we calculated is 0.0461. Like this, 0.0469. Okay, 0.0469. Okay, the option is actually 0.047. So it's okay. We have already calculated this. And finally, that the eigensystem thing. So find the condition number. This is important. Condition number K of which matrix? Obviously, exactly, because that everything is related to this. Okay, and also say that check, is there any serious problem? Serious problem of multicollinearity. So this is the only condition through which we can actually check. Other conditions are may reflect some values. It might not matter, but this you must always check. Okay, problem of multicollinearity. This you must always. So let's do. Okay. So what is your condition number? K is lambda max by lambda min. So here it's a two regression model. So you will get two lambdas, lambda 1 and lambda 2. So one of them will be higher, another will be lower. So you don't need to check the condition indices. Okay. So x prime x we have already calculated. It is nothing but 1.975492.975492, the correlation matrix on 1. Okay. And every time you calculate the condition number, always remember you have standardized that. Okay. Be careful. So how to calculate? I know this is the way we generally calculate the eigenvalue. Let's do it because it's a 2 by 2 matrix. Easier to calculate. 975492. 1 minus lambda. Okay. And this determinant has to be 0. Okay. Determinant of this A, suppose, determinant of A has to be 0. So we have 1 minus lambda whole square minus R12 square actually. So 0.975492 square. This has to be equal to 0. Okay. So if you reduce it, 1 plus lambda square minus 2 lambda minus point. This is we have calculated 9525 equal to 0. Further, lambda square minus 2 lambda solve further, it becomes 0.0475 equals 0. And this is easy. It's just a quadratic solution. So it is minus of minus 2 because b is minus 2. Okay. Plus minus root over b square minus 4 is c. So 2 square minus 2 square is 4 minus 4 into c into 1 divided by 2 into 1. Right. So lambda will be 1 is 2 plus minus root over this comes out to be 3.81 divided by 2. So one of the lambda, so is lambda 1 is the greatest one, which is, so it reduces actually 2 plus minus 1.5, sorry, 1.9519 divided by 2. Right, right. So lambda 1, let's see, the greatest one is 1.976 and lambda 2 is 0.02405. So these are the lambdas which we have got for the centered and scaled matrix X prime X. Okay, these are the lambda. So then what is the condition number? Lambda max by lambda min. So here it will be what? Lambda 1 by lambda 2. So K is 1.976 divided by 0.0240. So this will give you K as 82.162, which is less than 100. So criteria, you remember the criteria, K is less than 100 means no serious problem. See, in the eigenvalue case, you are getting no serious problem means you have to really believe that fine, multicollinearity exists, but not serious. Okay, but using variation inflation, you can see 21.7 is certain multicollinearity is there. It is showing. Okay, and R, the correlation. So the correlation comes out to be about 0.97, which is greater than zero point 0.9. So this is an important thing. Here, R is greater than zero point 0.9. R is greater than zero point 0.9 here. Okay, number one. Number two is that your variation inflation factor is greater than equal to 10. So this is also multicollinearity, strong multicollinearity exists. But eigen system K condition number shows that it is less than 100. So we will see this. So it's no serious problem. Okay. So this is the way the questions will come and some based on simple concepts which I have discussed. I think this is enough for today. Okay. So if you have any question, you can ask. Otherwise, I just say that what I have done today. So mostly after solving the assignment questions, we started the concept of multicollinearity, where we have seen that whenever there is a linear dependence of the regressor variables, you find that determinant tends to 0. And that results into problem of multicollinearity. And we have seen one of the examples, also it is there. And we have discussed several problems of multicollinearity. And to detect the multicollinearity, you must always do this technique, centering and scaling of the regression data using this concept which I have shown. Okay. Once you have reduced this, you can calculate this, where x prime x will be a correlation matrix for a your 2D case or two regression case. Okay, two regressor cases. But more than two regressors, you can always compute the uh, coefficient of multiple determination. We have seen that the variance is a criteria which is very strong, and one of the detection criteria is the variance inflation factor, which is 1 upon 1 minus Ri square for greater than 2 regressors, or 1 upon 1 minus R12 square for 2 regressor model. Mostly the questions are with 2 regressor models, so best to use the correlation. And these are the criteria for VNES. If it is greater than equal to 5, it indicates multicollinearity. Greater than equal to 10, it says certain multicollinearity. So other problems we have discussed here, and then different detection techniques. Again, we have seen that correlation coefficient is one of the techniques, which is nothing but a threshold value. But this is the best, the eigensystem analysis, where we calculate the condition number, which is lambda max by lambda mean. For a two regressor variable, there are two lambdas. It is easy to find lambda max and lambda mean. But if you have more than two regressors, you have to check for each and every indices. And we can do it in this way, where lambda max we will find out from all the lambdas and then take the ratios. Criteria here is this: k is less than 100, no serious problem. In between 100 and 1000, moderate to strong, and k greater than 1000 is a severe problem of multicollinearity. And to deal with multicollinearity, we can increase the number of samples, we can remove regressors from the model and collapse variables. Okay, and that's all. We have solved a practice problem. We have seen how to do the centering and scaling, and we have calculated the correlation matrix just by multiplying. Okay, so based on that, we have solved the question. Yeah, okay, it's clear. That's good. Good. Okay, fine. So if there are no questions, then we can stop. Okay, thank you, everyone.